Alright, welcome back to another video by Firestarter Graphics and Engineering. Welcome to the new year. So, we're going to start the new year off with a bang. We're going to start talking about rocket fuel. First thing we're going to talk about today is characterizing rocket fuel. I am not going to teach you how to make rocket fuel. However, two people that I trust to show how to do that correctly is Rotary Rocketry and The Rocketeer. Go visit their channels and go learn how to make basic sugar fuel. That is a good place to start. Eventually, you can move into the ammonium perchlorate, but starting with some sugar fuels is a nice place to start, especially for learning how to characterize fuel. And now you're probably asking, well, what the heck is characterizing? You keep saying it. Tell me what it is. Okay, characterizing is learning the behaviors of the fuel so that when you scale your motors up, you don't run into crazy issues, that the behavior stays the same. And so there's an equation that represents that behavior, and it's called the burn rate equation, where R, your burn rate, is equal to the burn rate coefficient or constant times the chamber pressure, and that chamber pressure is raised to an exponent. Now, I expect some knowledge of math here. If you don't know algebra, I recommend, highly recommending, learn some basic algebra so that you don't get confused or messed up and don't understand what's going on. Some basic algebra should be required to make basic rocket fuel, even if it's with sugar. So, okay, we have this equation. Okay, so what does this equation do? Well, let me show you at least a picture of what it looks like. This is what the equation looks like when it's graphed. I have these values here. I'll show you how to get these values here in a minute. These are our A and our N. You can see this graph. So this is burn rate over time. So, let's look at 1.4 seconds. So this is kind of how things look over time. Okay, great. Let's move on and get the math out of the way, because a lot of people don't like math. I like math. Now, I'd never teach it because I'm not a theory. I am theory. I like theory because I like what I can do with it. I wouldn't want to teach math. I would want to teach applied math. Like, hey, here's all this math that you just learned. Let's do something with it. And that's what we're going to do today. Okay, so the formula we're going to be dealing with is a flexi fuel formula. 65% oxidizer, which in our case is potassium nitrate, 18% corn syrup, 17% sugar, which has been finely milled into powder. You can use powdered sugar or table sugar and powder it up yourself. Now, there is cornstarch in regular powdered sugar that can absorb moisture quickly, so make sure to store your motors in with those little desiccant packets. And I also think you can store them in rock salt, in a container with rock salt or ice cream salt, and that should absorb moisture as well. Anyways, okay, so first thing we need to do is find the density. And usually we can just say, well, I know the density of one substance, but how do I find it if I'm just doing percentages? You literally just take the percentage and multiply it by the total density of that product. For example, potassium nitrate has a density of 2.11 grams per centimeter cubed. Times it by 0.65, you'll get a number. Do the same for the other three. You'll end up with 1.74 grams per centimeter cubed. Convert it to empirical, because open motor and other things we'll use can use either or, but I'm just showing you converted at 0.06. It's a little bit longer than that, and we'll get the longer number later. Okay, so to fully characterize fuel, we need to solve for A and N. Alright, but that means we have two unknowns to solve for, which means we need to have two equations, because for however many unknowns you have, you need that many equations to solve. One unknown, one equation. Two unknowns, two equations. Three unknown, three equations, so forth. You see the pattern. So how do we do this? Well, that's when you do your static testing. And you only need two successful static tests. Make sure that the pressure differences, and I'll show you how to calculate the pressure, inside the casing is a big enough difference. I usually aim for 150 to 200 pounds per square inch difference between two burns. And you change that pressure by changing the nozzle diameter. So, let's look at test number one. Grain diameter, core diameter, grain length, all the stuff that you should know. Nozzle throat diameter. So number 27. Okay, what does number 27 mean? I actually had no idea what this meant. I thought it was like drill bits. Okay, number 19 meant something specific. Like I thought it was the same standard as a number 27 drill bit, but it's not. It just means it's this number divided by 64, or this number times 1 over 64. So my burn time was 1.33 seconds for the first test. My burn rate is this equation, okay, web thickness divided by burn time. Now you're thinking, wait a minute, you just said this was burn rate. That's true. This is the theoretical model right here. This is a very accurate model too. This is burn rate, a physical, analytical, empirical test, the empirical burn rate based off of empirical testing. So the web thickness is your grain diameter minus your core diameter. Now you want to divide that by 2 because we want to focus on the radial measure, or times it by half. And then you're going to take this value and divide it by 1.33 seconds. You'll get millimeters per second, but I converted it to inches per second. So here we go. Okay. Now we have Kn. If you're not familiar with what Kn is, that is the ratio or division or a fraction of your burning surface area divided by your throat diameter of your nozzle. So you can calculate that. It's just basic surface area equations. You can Google all of them. Now remember, with a grain, you have the top and bottom surface burning as well as the inside core diameter. But the outside wall is not burning. It's inhibited, is what we call it, because that's what's touching the case. All right. But, however, if you visit this gentleman's website, jamesyon.net/kncalc, download the Bates calculator, open it up in Excel, you can put in your grain information. I'll do a video later on some basic grain theory of what is a good starting place. I will just say the 1:3:5 ratio is one that I kind of came up with that is excellent, but we'll discuss that later. Anyway, so you put in your information, it'll go ahead and calculate the Kn. You want your first Kn from before it starts burning. You don't want to do it mid-burn, you just want your first initial Kn. Alright, great. So now we have this Kn value, then we have our specific impulse. This is calculated from an equation based on your static test. Go look it up, find the equation. Mine happened to be 120.00 and some change, so I just left it at 120. Chamber pressure, this is the P in the analytical, no, the theoretical burn rate right here, the chamber pressure. And it's calculated numerically by your specific impulse times the Kn density burn rate. Gives us 382.82 psi. This number is important. Okay? All right. Now we're going to rearrange R for A. It's a little bit easier. You can rearrange it you can leave it as R and then still set them equal to each other. It depends on how you want to do it, but I find it easier to solve for A. So then just leave it right there because we know we need two equations because we have A and N we're solving for. So let's move to test number 2. Everything stayed the same except the throat diameter. And the burn time changed. Okay, go ahead and recalculate. Burn rate, we get 0.47 inches per second. Kn is different now. ISP stays constant. If you don't understand why or see why I'm keeping it constant, that is A-okay. Go find Sutton, his propulsion engineering book by Sutton is his name. It is free. They do have it on Internet Archive. Some older editions. I got the 9th edition. And it is legal. And some schools actually have permission to post it online for free for other people to use. I got mine from MIT. I didn't go to MIT. Let me rephrase that. I got mine from MIT. However, some of my professors taught at MIT for 20 years. And so education's education, right? I mean, it's once you hit a certain higher education, it's, especially in engineering, it's, pretty much all kind of the same. Anyways, so, or you can use ChatGPT to ask certain questions. Now, excuse me. Plug everything in, solve for A. Now we have two equations, now our two unknowns. Set equal. And you can go ahead and pause and just kind of see what I'm doing here. Cross multiply, rearrange, so that pressure is with pressure, rate is with rate. See right here. Pressure with pressure, rate with rate. And if you've done it right, the higher rate and higher pressures will be on the numerator of the fractions. That is very important. If the tests were not too drastic enough, you'll end up with either the lower number on top, which won't work because when you take the logs, you'll get negative numbers, and that's bad. Or you'll have higher numbers on top, but it's too close to each other that you end up with n of like 1.67, which you don't want n above 1. And you don't want a above a certain number either. I mean, there's a specific range it should be. So you need to make sure there's a drastic enough in the pressure, and that's why 577 versus 382 worked out great. It was, perfect for my tests. Okay, so take the logs. We end up with n. Back substitute it into the original equation, solve for a. So we have n and a. Excellent. Now what do we do? That's a perfect question. The next thing you need to do in order to characterize the fuel and validate your information, we need to see if these are actually correct because they might not be. And that's what we got to do right now. You need to download two programs, ProPep 3 from GitHub and also OpenMotor. Now, ProPep 3 is awesome. It was originally done in the 70s, and a gentleman at NASA took all the propellants, all the ingredients propellants, I should say, and he knows the specific heat and all these values like K value, specific heat, latent heat, and all these things. If you've ever taken thermodynamics, you know what I mean by when I say table lookups. So they get these by putting them in what they call a bomb I can never say it right. A bomb calometer or kilometer, not kilometer as in a distance, but take calories, the unit that our food is based in. And what they do is they put it in this pressure vessel and they burn it, and they can detect how much energy is given off when it's burned. And in our body, that's called metabolism. So that's how they figure out how much calories is in food. It's the amount of energy when it's burned in a vessel. So they do the same thing with chemicals and ingredients. So if you go to My Documents, ProPep 3, you can actually see this pepcode.daf. Open it up in Notepad++, and you can see all the table information for each ingredient. And this is what is used for ProPep 3 to calculate some stuff. So let's go ahead and actually do that. All right. Okay, ProPep 3 is open. I've put potassium nitrate, dextrose, sucrose. Now it says weight, and I've just converted my percentages to weights. So 65 grams, 18 grams, 17 grams. So you can see the relation 65%, 18%, 70%, 100%, or 100 for whole. Left the default operating conditions. So the exit pressure, what that means is chamber pressure as it's going through the nozzle, the exit pressure as those molecules exit, they hit regular standard atmospheric pressure. A lot of people think that the pressure is going to be much higher, and that's how thrust works and everything, but it's not. The pressure will just be atmospheric. Look up in Sutton's book, Nozzle Design Theory, and then also learn about thrust and how it relates and differs from pressure. Anyways, okay, when you put in these numbers, hit boost velocity nozzle design and then hit calculate. It's going to give you your specific impulse. Star means for vacuum. And then your characteristic velocity of the exhaust, which is 3,013.89 feet per second. Gives you your density and your molecular weight, I forget what this is called, some sort of ratio, but this is important. And then your chamber temp. If you want more results, go ahead and hit display results. And you can use these for maybe a design report or something, but it's not needed for characterizing fuel at the moment. Okay, so what do we do with this? This is information we need to put into OpenMotor so that we can actually start graphing how the motor behavior works. Go ahead and open OpenMotor. I've already put in my Bates grains information in my nozzle based off my tests. We're going to go to propellant editor. Then you're going to hit new. In my case, I already have one, so we're going to hit edit. And in yours, it's going to be scrunched up like that. You can't see it. You just need to drag the bottom down. Okay. Density. This is the density that I calculated. 0.06286 pounds per inch cubed. Minimum pressure of my case, 0. Maximum pressure of my motor case, manufacturer says 1500 is the safe max. Burn rate coefficient, this is the A that we calculated, 0.123. 0.123, right here. Then N, 0.21, will be put right here. Now, it should say 6. There was a 6 at the end of it, and I should put that in the document. Specific heat ratio, that's the ratio, 1.13. That came from ProPEP. So did the combustion temperature and the exhaust molar mass. Okay. Now, as you change these, notice this characteristic velocity. I can't input that, but it's based on your burn rate exponent. Whoops. It's based on specific heat. Burn rate coefficient sometimes has a effect on it. Combustion temperature has an effect on it, and some other things, and the molar mass. So these things contribute to your characteristic velocity. Now, look how close we are. 3,014 feet per second. 3,013.897 feet per second. That's almost spot on. That's pretty good. That's a decent validation, but let's do one step further. So let's go ahead and open motor. Well, go back to it. I'm going to hit cancel because I don't need to save anything. It's already there. Now with all my information input, I'm going to go ahead and hit simulate, run simulation. This is what the burn will look like of my motor over time. Okay, what is my peak pressure? 381.81. What was my calculated pressure? 382.82. Pretty dang close. That's a pretty good indication that our burn rate numbers for N and A are really close and pretty spot on. So let's look at some other things. The initial KN 137. Let's see. Let's go up 170 for that one. 123. So a little different, but not too bad. Burn time 1.32 seconds. My burn time was test number 1, 1.33 seconds. And this is for test number 1. I should state that. Sorry. 382, 1.33, 123, and 137. So not bad. So that is how you can validate your numbers if you're trying to characterize fuel, which is awesome because now we're just pretty spot on. So now I can change things. Now I know that my propellant is pretty decent. So another thing that you could do is buy a cheap analog $15 pressure gauge. Some of them have glycerin in them. You'll want to drain the glycerin, and then you can make a test stand. You can find it on, I think, NACA's website. Well, he makes a pressure stand for the rocket motor using one of those analog $15 pressure gauges. And then you can record it with your phone, the burn time, as well as what your pressure is throughout the burn time, and then you can resolve for A and N and see how close you were. But for a pretty good, I don't even want to use rough guesstimate, but for a pretty good guesstimate, this is how you do it if you don't have a pressure gauge. So anyways, kind of fun. I know it's kind of a long, dry, boring video, but it's kind of an interesting way to validate all your hand calculations to see how you've done. So with that information, continue learning and moving forward and build some dang rocket motors. Anyways, thanks for watching and see you next time.